Welcome back. This is the second lecture and we are going to study fluid properties again. So in the last class we studied mainly the shear stress and fluid viscosities. So today we will proceed a little further. This is for course called hydraulic engineering. So as we said that viscosity and other concepts are for all fluids, and gas is also a fluid. So we will also see what a perfect gas law is. You have studied that already in your class 10th and 12th, but these first 10 lectures are going to be a revision of your basics fluid mechanics course. So I'll go a little fast because I know you have already done it in your previous course called fluid mechanics, but to make the course more complete, these topics are going to be covered again. So what does it say? If you remember, it says PV is equal to nRT, okay, where P is pressure, V is volume, R is gas constant, T is temperature, and N is the number of moles. R is a universal gas constant. Temperature is taken in Kelvin. The value of R is given as 8.314 Newton meter per mole Kelvin. In the text, one of the textbooks that we are referring, Munson, Okishi, Young or Sengel, the R in the text has been written as R divided by m molecular mass of the gas, where m gas is molecular mass. M gas for air is 0.029 kilogram per mole. Can you guess why? Why is this M gas for air reasonable? The reason lies in that air comprises of almost 80% nitrogen and 20% oxygen. The molecular mass of nitrogen is 28 gram per mole and oxygen is 32 gram per mole. So I am going to so if you see this 32, this 28, so this is 80%, okay, this is, so this is how this value will come, okay. So proceeding to the next slide, one of the important other property in terms of gases is bulk modulus of elasticity. So what does bulk modulus of elasticity do? It relates the change in volume to the change in pressure. So bulk modulus of elasticity is defined as so you see EV is d minus dP dV by V. This is the definition of bulk modulus of elasticity. Yes. So we are going to the highlighter now. So this is the equation that we are going to come later, okay, and how do we get it? This is shown here after some more description of bulk modulus velocity. The changes in density at high pressure, for example, in terms of pressure waves, is an example is a sound wave and other is a water hammer. So now I promised that I will show you how to come from this equation to this equation. So we already know PV is equal to constant. So on differentiation we will get P dV plus V dP is equal to 0, and if you take P dV to the other side and do dP dV, it comes out to be minus P by V. Hence EV can be written as, if you use this equation and substitute the value of dP by dV, so putting these two equations together we will get EV as pressure in this case, okay. We can also say that y dp divided by dv by v can be written as dp by rho. So I will just go and now so if you see this equation, dp by dv is equal to minus p by v. So we can, if you bring p on this side and dv, so it's dp by p is equal to minus dv by v, and this minus dv by v comes here, and therefore ev can be written as minus dp, and dv by v is written as minus dp by p. Okay, sorry, dp by, yeah. Yes. No. So this becomes pressure. Okay, so now we proceed to the next slide. So how much does the water compress? It's the same equation, dv by v is equal to minus dp by ev. So this is the figure which shows the bulk modulus of elasticity, how it varies with the temperature. So as you can see, the bulk modulus of elasticity increases as the temperature increases to a certain value and then starts decreasing. These are the normal ranges of temperature in air. 100 degrees is very rare, but the most common ones are 0 to 30 degrees. In India it can be 0 to 40 degrees. So for water, so I'm sorry, this bulk modulus of velocity is for water. So compression and expansion of gases. So one of the phenomena is isothermal, which is constant temperature. So what happens is PV is equal to nRT, that equation we already know. So PV is equal to nRT. So PV by N is again RT, which is constant. Okay. So this is RT. So V by N is directly proportional to 1 by P or inversely proportional to P, where P is absolute pressure and V is specific volume, and therefore we can also write P by rho is also constant. So we need to find out dP by d rho for to be able to find out EV, because EV is given as dP divided by d rho by rho. So P by rho is a constant, right? So so is dP by d rho, and dP by d rho when substituted, it will give us EV is equal to P. So more importantly, for isothermal process, what you must remember is that EV is equal to pressure. This is most important finding of this particular slide. Okay. So we are going to look at another phenomenon or process called isentropic, where no heat is exchanged. In this case, the equation for isentropic process is given by P by rho to the power k is equal to C, where k is Cp by Cv. This is a very standard terminology in thermal physics that you have already seen in your class 10th and 12th. So this is also called a specific heat ratio. So if you do dP by d rho from this equation, you will get C k rho to the power k minus 1. Therefore dP by d rho will be P divided by rho to the power k multiplied by k rho to the power k minus 1. We are using the substituting the value of C in terms of P by rho to the power k, and therefore dP by d rho will come out to be kP by rho, or we can also write EV, because EV is given as dP by d rho by rho. Therefore, we have got dP by d rho as kP by rho divided by rho. So, we get kP. More importantly, EV in case of eccentric process is given by kP. K is specific heat ratio. So, for isothermal process, just going back, EV is P, and for eccentric process EV is kP. That is very important to note. Okay. So, another important thing that we should be aware of, speed of sound. Speed of sound C is given as, this is the formula, dP by d rho, and EV we know that it is dP divided by d rho divided by rho. Now we have to solve for dP by d rho. We already know from this equation that EV by rho can be written as dP by d rho, right? Therefore, if we put this equation in this equation, then we can get C as under root EV by rho, where C is generally very large for compressible. I mean, it is very difficult to compress fluids, because EV in case of fluid is too much, the bulk modulus. So, we should be, if we know this equation and we know what type of process is there, we should be easily able to find out the speed of sound. So, another concept is vapor pressure. So, this is the variation of vapor pressure along with the temperature. As you see, as you keep on heating the temperature, the vapor pressure increases to a great extent. At 40 degrees, it is over 7000 Pascal. You would have observed that on heating the water, the molecules are easily able to escape. So, this is due to the vapor pressure. And to be, some of the key values that we must be aware in these type of courses is, for example, what is the vapor pressure of water at 100 degree centigrade? It is 101 kilopascal. So, this is an important value to remember. Okay. Another such property is the surface tension. An example here is that the pressure increases in a spherical droplet. This is the surface of a droplet, for example, and this is surface molecules that we are actually seeing here, and the phenomenon that's going to happen if you closely area between these two molecules, that we are enlarging and zooming. So, what is happening is there are two type of forces. So, there will be force delta P into pi r square due to the pressure difference, and the force of surface tension that will be resisting, it is going to be 2 pi r into sigma. This is the standard surface tension that you have read from before, but I am repeating it again. So, in case of force balance, what is going to happen, that this F sigma delta P into pi r square should be equal to, so this is F sigma should be equal to the pressure force. And what does it give? It gives the pressure difference in the droplet is 2 sigma by r. This is surface tension. Okay, radius is radius of the molecule or the drop or the bubble, whatever that is. So this, as you can see from this curve, as soon as you increase the temperature of the fluid or water, the surface tension is going down. So we have included an example of surface tension here. But estimate the difference in pressure between the inside and outside of bubble of air in 20 degrees water, 20 degrees centigrade of water. The air bubble is 0.3 millimeters in diameter. So we already know the equation here. Sigma is given as 0.073 Newton per meter, and R is the radius 0.15 into 10 to the power minus 3. We have already seen the equation. Delta P is 2 sigma by R. So delta P 2 sigma is the value here, and R is 0.15 that we have come up with this. So the pressure difference comes out to be 970 pascals. I think it's very simple to calculate, so you can use your calculator or just here. So what is the difference? What is the difference between the pressure in water droplet and pressure in an air bubble? So this is a question for you to think, but just a hint, it has something to do with the number of surfaces of air and water droplets. So this normally, the revision of our fluid properties is complete, and the basics that we have seen. So I try to have a review in such cases where we are revising something. So what we have done, we have read about viscosity. We have read that tau is equal to mu du by dy. This is one of the most important equations actually. We have read about density and specific weight. Density is rho, specific weight is gamma, that is rho g. We have read about elasticity, bulk modulus of elasticity, EV is dP by d rho by rho. We have seen that for eccentric, we have seen that for isothermal and eccentric, and we have also related that to the speed of sound. We have seen about vapor pressure, we have seen about surface tension, and this was one of the important equation, delta P is equal to 2 sigma by R. So to review the properties, viscosity, density and specific weight, elasticity, vapor pressure and surface tension, these are the important properties that we have read. Now I have included for your convenience 4 different problems encompassing all the concepts that we have done. So we will go into these questions one by one. So the question says, in an experiment, the tip of the glass tube with an internal diameter of 2.0 millimeters is immersed to a depth of 1.5 centimeters into a liquid of specific gravity 0.85. Air is forced into the tube to form a spherical bubble just at the lower end of the tube. Estimate the surface tension of the liquid if the air pressure in the bubble is 200 Newton per meter square. So how do we approach this problem? Okay. So first and the foremost thing that we should be doing is drawing the diagram, and whatever piece of information that is there, we need to, so what it says is, so this is water and this is air is coming here, this is the bubble, that is 2 millimeter diameter, right? This is 2 millimeter dia and this is 1.5 centimeter. Yes. Okay. So the pressure inside the bubble is given as 200 Newton per meter square, right? And it is also told pressure outside the bubble is given by 1.5 into 100 into 0.85 into 9790, that is the specific weight, right? You see this length 1.5 centimeter here, so 1.5 divided by 100 and 2.85 is the specific gravity and this is a specific weight. This comes out to be 124.8 Newton per meter square. So what is the pressure difference now between inside and outside? Between inside and outside the bubble is 200 minus 124.8. So this is here and this is here, okay. All right, and this pressure difference comes out to be 75.2 Newton per meter square. So what was the formula for the pressure difference that we have seen in couple of slides before? That delta P is equal to 2 sigma by R, right? So correct. So using this equation, sigma can be written as, or we just substitute the value. This value is 75.2. This is equal to 2 sigma divided by R. R is 1 by 1000. This will give sigma as 0.0376 SI units. So this is one of the examples of the surface tension forces. We can now see that in this we found out, we'll select the pen and then this sigma here came out to be 0.0376 SI units, okay. Now we go to the next problem. It's also very much related to the surface tension. So the problem says a very small quantity of liquid having a surface tension sigma forms a circular spot of diameter d between two glass plates separated by small distance h. Obtain the expression for the force required to pull the plates apart. So as I said, the most important thing to do is to be able to draw whatever is given, okay. So let's draw one plate, two plates. So this is the plate, this is liquid, this is given by H, and this distance diameter d. All right. So these are the some of the figures that we already know. So now what we say is, let the pressure difference between the ambient and that in fluid within the plate gap B delta P, right? Then delta P can be given as P1 minus P0, or pi dH delta P can be written as 2 sigma pi into D, or delta P is equal to 2 sigma by H in our case. So if force required to pull the plates apart is F, F can be written as pi d square by 4 multiplied by delta P, right? And 2 pi d square sigma by, we substitute the value of delta P, or it can also be written as pi by 2 d by H sigma d. Sorry, I'll write it again. Pi by 2 d by H sigma d. So writing the final equation here, F that is required will be pi by 2 d by H sigma d, sigma multiplied by d. Okay, now we go to our next problem, that is related to the air and the compression, so mainly related on the gas laws. So air at 20 degrees centigrade and 200 kilopascal contained in a cylinder is compressed to half its volume. Find the pressure and the temperature inside the cylinder if the process is isothermal, and B if it is isentropic with K is equal to 1.4. So okay, the best way to go is to have the whiteboard. So whiteboard is very good. So in isothermal process, P1 V1 is equal to P2 V2, therefore P2 is equal to P1 V1 by V2, or 200 into 1.0.5. This is very simple to calculate, and this is 400 kilopascal absolute temperature, right? Because everything is given here. Because this is isothermal process, temperature will remain constant. And therefore T2 is equal to T1 is equal to 20 degrees centigrade, right? The second part, in isentropic process, What happens in isentropic process? PV to the power k is constant. So in this case P2 will come to be P1 multiplied by V1 by V2 to the power k. So 200 into, this is 0. It's compressed to half, so volume to the power 1.4, and if you calculate this it will come to out to be 527.8 kilo Pascal. Okay. Now for temperature, PV is equal to RT and PV to the power k is constant, right. So we can use this equation here and then we can write RT V to the power k minus 1 is equal to constant. So I'll do the get the next page. Okay. So if we use, so what we found out in the last screen was RT V to the power k minus 1 is equal to constant, or we are also able to write T2 by T1 because R will be cancelled on both sides, V1 by V2 divided by k to the power minus 1. We know that T1 was 20 degree centigrade, or in Kelvin it's going to be 273 plus 20 is equal to 293 Kelvin, and V1 by V2 is 2, and k minus 1 will give out 1.4 minus 1 as 0.4. So on substituting these values we can get T1 is equal to 293 into 2 to the power 0.4 or 386.6 Kelvin, or T1 is 386.6 minus 273, that is 113.6 degrees Celsius. So this is the temperature that we have got in case of eccentric process. So what I would like to do is I would like to end our fluid properties lecture here. If I get more time we can solve one more problem at the end of this week's lecture. Okay, thank you so much. See you in the next week lecture, that will be on fluid statics and that will be spread over 3 different lectures. Thank you so much.